So let's talk a little bit about some horizontal and vertical stretches and shrinks here that come from this section. Suppose I've got some function here that that is periodic and looks something like this. Extends out to 4 in the positive x, down to -4 in the negative x direction. And if I have a horizontal shrink by a factor of 1/2, imagine slinking in each side toward the y-axis by a factor of 1/2. So the 2 is going to become a 1, the 4 becomes a 2, and my vertical height, however, doesn't change at all. Same thing on the left side. -4 gets taken into halfway into -2, and the -2 gets taken to -1. So that's what we mean visually by a horizontal shrink by a factor of 1/2. So how about if we take our original function back there and we do a horizontal stretch by a factor of 4. That means my original 2 is going to be stretched out to a 4, and my original 1 is going to be stretched out to a 4, and my original 2 will be stretched out to an 8. My vertical does not change because I'm stretching horizontally. And again, if I want to do it algebraically by my rule, a horizontal stretch by a factor of 4, drawing the graph out further away from the y-axis, stretching it, results in me replacing x with a quarter x. So if I replace x with x minus 3, that results in a horizontal shift by 3 units to the right. And again, looking at my original graph, I'm going to take that -4, move 3 units to the right, takes me to -3. And my original, my original 2, if I move 3 units to the right, is going to take me out to 5. And if I was at 0, 0 before, I move 3 units to the right, that takes me out to 3. No horizontal shift, there's no change in my output, my y outputs, it's simply a horizontal shift. So if I want to look at what happens if I take f of -x, in other words, replace x with -x in my rule, that's going to reflect my graph over the y-axis. Now our original graph that we started back with there on the first slide, f, has symmetry with respect to the y-axis. So if I reflect something with symmetry over the y-axis, I get exactly the same picture out. So there's no change in how my graph is going to appear for this particular graph. Now, let's suppose I want to look at a function g of x, which is right here, and now I want to look at g of the absolute value of x. In other words, I'm replacing x with the absolute value of x. That's going to reflect anything from the right of the x-axis to the left of the x-axis, and it will eliminate any of the original graph that appeared in quadrants 3 and 4. Because if you think about it, if I'm looking at g of absolute value of 2, that's going to be the same as g of the absolute value of -2. So whenever I were to put in a negative x value, its absolute value would be positive, and I will get the same output as I did if I put the positive value in. And that creates y-axis symmetry. So what I'm going to do here in this case with g is reflect what's in quadrants 1 and 4 over into quadrants 2 and 3. And that original stuff is simply gone. That original stuff that appeared in the graph isn't going to appear for g of the absolute value of x. I'm simply going to reflect over what was in quadrants 1 and 4. Now, still looking at our function g from the last slide, if I'm looking at the absolute value of g of x, that's an absolute value of outputs. That's clearly going to maintain everything that was positive will still appear as positive because the absolute value of positive numbers are positive. But it will take all my negative values and reflect them over the x-axis to create the graph below. So this is g of the absolute value of g of x here. So if I'm looking at something like 3 times g of x, what I'm doing is multiplying each output value by 3. So if I consider my graph of g here from before, each output's going to be multiplied by 3. So outputs of 0 aren't going to change. 3 times 0 is still 0. But all my other outputs are going to be multiplied by 3, so I'm going to come up here. All these are going to be multiplied by 3, so I come down here. All these will be multiplied by 3 up here. all these are multiplied by 3 down here, and all these are multiplied by 3, so that's going to go up there. So again, it's simply this would represent a vertical stretch by a factor of 3 of my graph of G. Now, though we haven't spoken a lot about what happens when I switch x and y in a rule, in an equation relating x and y, haven't talked a lot about it, but what we've seen indicates that when we switch x and y, we get graphs that are symmetric about the line y equals x. And when we switch x and y, for example, what appears as a vertical line in f, if I switch x and y, that's going to appear as a horizontal line in the switched graph. And we'll learn more in the next section, in section 4.5, that indeed, if I switch x and y, I wind up with what's called the inverse of f, the undoing function from f. And if in f I had a vertical axis of symmetry, in the inverse I'm going to have a horizontal axis of symmetry going through the vertex.